And hi, so this is um, based on a talk I gave uh, 5.5 years ago at a conference, and I've just expanded a little bit and made some changes to it. So it's really, we'll get into it. It's using some elements of the Electrofaces workflow to model three ways from those Electrofaces. And I'll explain the categorical, e-facies, probabilities, and petrophysics with assignment in the talk. And yeah, so here we go. The talk was modified from this conference. And at the time, my co-authors were Mohan Shrivastava and Jeffrey Yaris. So I'll just acknowledge, Catalina, Terra X Group. She's had me do courses and talks, and then some of the software that people are providing me with these days. And then Halliburton's where I was when I put this material together, although I've been working on some of that material for a number of years. So the topics then are just a quick overview of facies as conditioning data, a little electrofaces background. So this is a quick background just to set the tone. And then we'll go over the data set we'll use and cover these three workflows. And we'll just touch on some of the checks and comparisons that are good for these processes. All right, so first, facies is conditioning data. Facies are used in the geomodeling scope and other areas to represent and honor reservoir heterogeneities. And heterogeneities include both the facies categories and the petrophysics within them. So this is the reservoir architecture described by the sequence of lithofaces and the variability of rock properties within each given facies. And we're looking at this as a categorical variable. It's treated as truth, as being hard data, and we know facies come from many sources. So here, facies, it's one word shared by many different concepts. And we have petrophysics, we have lithofaces, depositional, and it just depends on who's doing the work. Sedimentologists are going to be looking at ichnofaces and etc. All right, and then the next step is the electrofaces background to set the elements for the process. So here we have the electrofaces background, and I have recorded some of those talks. I gave one of them through Terra X, and I've put some recorded talks on YouTube just for reference. Okay, so the motivation then is that we want facies with consistent petrophysical properties for modeling, and that means we're inputting well logs, which includes facies curves, and these are described at different scales than the log resolution. So the goal of the electrofaces is to get the facies, well, one of them is to have facies at the log resolution consistent with the log. So we want to take into account stratigraphic and conceptual models and our intervals, zones of interest, and the transitions within them. And the facies, we want to account for the relative proportions and significant properties within those facies. So what are the facies trends and what are the reservoir properties? And we're also looking at a 1D to 3D modeling strategy. So there's a lot of other considerations when setting up models. And then electrofaces are calculated at log resolution with consistent properties as set. Okay, so the modeling approaches then, it's classification methods, and there are things like discriminant analysis, parametric type methods, and that's what this represents, that we're looking at, say, bimodal, multimodal distributions in individual parameters, and we're looking to discriminate and separate the classes. And so that's those are parametric approaches. Then we have non-parametric, say, Bayesian approaches. And the thing is that the parametric approaches don't handle the complex data shapes that we have. And so parametric approach is a little more simplistic. They can be handy for unsupervised approaches where you don't train with input facies from the geologist. So the Bayesian approach is one of the non-parametric approaches, and there's different implementations in the commercial software. But these non-parametric approaches adapt to the data distributions when we have different facies. And so here we're just saying that what is the probability of a new sample to be assigned, like of a new observation to be assigned to a particular facies class, and that's just the this non-parametric approach. Then I'm not going to go over this slide. There's commercial software applications, but for this talk, I wasn't using commercial software. I just had MoCode, Moshe Vastava, just set up a lookup table, and so we didn't adjust the facies to honor proportions explicitly. Like there's some bells and whistles in commercial software. So I'm going to just touch on preparing the data, and then we'll go into the main part, this multivariate geostatistical set of workflows. So we have the electrofaces analysis and exploratory data. Analysis is really a topic from geostatistics and setting up geomodels. And we're going to use this Hadron data set. So here we have 4 units. We're going to look at the bottom red unit because it had the 4 facies, and we avoid dealing with trends across the other units. So we have 4 facies. Our training set, where we have facies defined, is this many samples, and then we train up additional well log footage, and the total then is 2732 samples. And the training data cleanup is really about getting rid of outliers. So for a given facies, removing the tails on distributions of things like gamma, density, neutron. And we do this kind of work when we have geomodels. So doing it, the cleanup when we build our facies models saves us from having to do a lot of that in the modeling steps. But here we also accounted in this data set for a bimodal depofacies split where we had mixed lithologies. Okay, so exploring the data, I don't really want to go into all these details. It's in the other talks. But we, as I said, we looked at the distributions, we looked at splitting, and we removed tails. Okay, that's the key thing. So here's the example. We have distributions for each facies of different properties. Here we have gamma, density, neutron, acoustic impedance. The depth was not matched, and we have here a bimodal distribution on one of the facies. So we have low to high gamma, two modes, and on inspecting the logs, I thought this mode should belong with another facies, so I removed it and lumped it with the other one, so I had a more distinct petrophysical distribution for this this facies here. The other option would be to drop that extra mode and let it reclassify naturally in the training process. And again, this data set, I didn't have a geologist to discuss it with. Normally I would discuss this with the geologist, but my thought is that these were defined more as depositional facies, and so it had multiple lithologies within that facies class, and that's why it needed to be broken. Okay, so here now we're getting into the meat of it, to set us up for this these three workflows. So we have the first part here. I just used the three curves, gamma, density, neutron, and cleaned up facies. We had a more exhaustive facies interpretation, and as I said, it was there were a larger scale concept interpretation, and so they were quite multimodal. And there you see a lot of cleanup of the tails, and that's what we use for the training. This then represents right here the training set, so three curves, cleaned facies. And from that, we had four facies, so we get four facies probabilities. And this comes out of the classification process. And so the highest probability on a depth becomes the final facies, the maximum probability. So here we have a lot of yellow, high probability here, and lower in the others. We have some blue showing up, and here we have some red and blue mixed. Okay, and notice the red and blue, and I think that's a consequence of removing a tail or removing a mode and lumping it with the others. So that would be what's coming out of this scenario. Okay, so then that's the last element is the electrofaces itself. And this is what we'd normally use in our modeling. Now it's consistent with the well logs. It's petrophysically consistent. But the whole subject of this talk is less about electrofaces. It's just assuming that electrofaces are acceptable and that we're going to proceed to use these three elements, the curves, the probabilities, and the actual electrofaces for three separate modeling workflows. And I'll just note that because we didn't use commercial software, I mean, this is typical. We adjust this in commercial software, but we didn't attempt to match the output proportions to the input training set. So we usually use the input logs as a guide to the proportion of facies. We're training them up. So here's the input training set. Here is training. Now we have a model, and the proportions have drifted a bit. So this one has gone down. This one's the same. This one has gone down quite a bit, and this one has gone up. And then once we apply it to all the log coverage, we get a different set of numbers. So we can, in commercial software, adjust the posterior weighting to shift it to be closer to the input. And that's a nonlinear process, so we don't try to match it perfectly. And anyway, we actually have a biased sample set, so we don't want to match it perfectly. But this is natural to see this kind of drift. Okay, so that said, we have the three workflows. We're going to look at a pixel method, plurigaussian, from the e-facies. Then we're going to look at the electrofaces probabilities, the 4 probabilities. And finally, use the 3 curves and co-simulate. So this is to build 3D models directly from each of these elements. And it sets up some interesting problems related to multivariate, nonlinear relationships. All of this in the machine learning space is of interest. I mean, this is very much a domain subject looking at facies, but it is a machine learning set of problems here. So the assumption then is that we're using these 3 elements as regionalized variables. So this is terminology from geostatistics saying that it's variables that have coordinates that are sampled from a larger random function, and that we're just looking at some sampling. Our data is a sampling of some larger random function model that exists in space. So reality is just one sample set. We don't know what that is. So here we go. We got workflow number 1 is going to be off the electrofaces. Workflow number 2 will be off of the 4 probabilities. And these aren't, these add up to 1, so they we'll have to consider that, and they're not usually treated as direct variables. So we're making some assumptions here. And then finally, the 3 curves. And the interesting thing about using 3 curves like this and building a 3D model out of these logs is just to say that if we're using well logs to forward model things like geomechanics, geophysical properties, this gives us an opportunity to use the logs themselves, build 3D models, and then from those do the forward modeling on the 3D space, so we don't have to deal with these nonlinear scale changes that are a problem if we're using, if we're trying to scale up these other parameters. It's just a little digression here. So workflow 1, plurigaussian simulation. So we're using element 1. So facies indicator methods, we're focusing on the pixel methods. So we have in my courses I cover the details of these 4 methods. So we have truncated Gaussian. The truncated plurigaussian is going to be the one in this talk, and it's an extension to two random Gaussian models, truncations. Sequential indicator is one of these 2 old methods. It's commonly used, and then multipoint is an extension of that we should be using more of. So here the idea of the truncated plurigaussian is that we have two sets of spatial models. We can have different varigrams, scales, and then these are combined. Okay, that's the simple way to say it. It's a superposition of processes. What this does is it allows us to reproduce facies transitions. And that's going to be the end of the talk, is looking at honoring facies transitions, and we really won't have time to discuss entropy measures. That'd be another talk. But we're going to look at this gets out of scope for all of the workflows, the anisotropies and shapes, but this is one of the key aspects of plurigaussian. So then plurigaussian itself, we have to set up rules for the truncation. We have 2 sets of truncations, and we're really looking at the nature of the transitions in the data. And so some refer to these as masks, this diagram, or rules. And So I call it a rule set, and this is the transitions we're looking at. So we have two Gaussian random function models. Those are tied back to variograms. And we have two sets of transitions. So here it's just saying that facies red is going to, in the primary variogram, is going to transition into blue and then yellow, from blue to yellow. And that red could also transition into orange. And then that's shown by these transitions here in the template. Then the second variogram model in Gaussian random function governs the transition of orange into yellow and blue. So it can have a different shape, anisotropy, and spatial structure. And so we can set up a correlation between those to soften or blend the transition sets. So what does it look like in practice? Here's that same transition rule set, and here it's with a zero correlation coefficient. They're independent. And it's showing that red facies in this circle, it illustrates that it can transition into blue or into orange, and doesn't really touch the yellow. The yellow is separated. And so we see that as the dominant feature. The red is encased in either blue or orange. Well, if we increase the correlation, go to a correlation of 1, it's reverting to a truncated Gaussian, and it's then red to orange to blue to yellow, and that's what we see here. The red is now encased in orange and then transitions to blue and then yellow. So that's the correlation of 1, or close to 1. And then the negative correlation flips it towards red, blue, yellow, then orange over here. And that's the dominant feature. So the point is we can control transition statistics. This is very important to sedimentologists and how we model how flow behavior works in the reservoir. So now, just to give an example, it's a snapshot from one of my courses on the whiteboard, my sloppy writing. But if we have a facies log, transitions, if we set up a transition table empirically, then we're looking at a transition from facies 1 to one of the other facies, or 2 to the other facies. So it's from 2. Here, if we go from the bottom, we say facies 1 to 1 is one transition. That would be a tick mark there. 1 to 2 puts a tick mark there. 2 to 1 is 2 to 1. So we keep going through 1 to 2, 2 to 1, 2 to 3, and we keep adding these up. We have 12 transitions, and then we can get the probability or the fraction of transitions. So that's something that most modeling algorithms don't account for, but we're using it to set up a rule set. So here's this data set, this hydrogen field data set. We have the 4 facies, or lithotypes, as they're called in the Isidus and Isidus Neo from geovariances. And this is the rule set. And it's showing, this is just a histogram representing the table. And so in facies 1 here, it transitions into red and yellow, and but it doesn't have any transitions into orange. It's 0 here. So it transitions mostly into itself and then into the others there. Then we have facies number 2, and that's orange. It does not transition into 1 or 3, into red or blue, only into yellow. And then facies. 3, the red, transitions into to 1 itself, and a little bit into the yellow. So from that, I set up this template with the orange separated from the red and blue, and red and blue transitioning into one another. If you notice here, red mostly transitions into blue in itself with a little bit into yellow. And then finally, the yellow is in the middle. It transitions into all the others. Okay. I'm just going to see if I can. I'd like to. Okay, that's not helping. Oh, that's better. Okay. I was going to turn off my share drive backup. I forgot it's continuously going to the OneDrive, and it's probably causing the screen lag here. And I don't want to turn this off, so I'll just keep going. So the setup then is shown there, and just to reiterate, we have the 2 Gaussian random functions, and the truncation sets here, slightly different transition set here. And this slide actually was from another talk I gave the next year at the Geostats Congress, where I go directly, like it's all about Gaussian. So then in that workflow, to finish off that workflow, we have, we set up facies trends. These are 3D proportions, and we apply that Gaussian rule set, and we have a simulation that shows us mainly red and blue in contact, mostly transitioning into yellow, and then into orange. So this is the key part of this workflow. The transitions, if we check them at the end, this diagram shows us the proportion of transitions in the 3D model. We go from blue to yellow, blue to red, quite a lot, and then some of the orange over here. And so we have here orange transitions almost exclusively into yellow, and we've removed the transitioning into the same facies just because it's so big. So this is the showing that we do get some stochastic results and some transitions into the other facies, and that, you know, the proportions do vary laterally, and it's a stochastic process. So again, red transitions mostly into blue and yellow, and yellow into all 3. And again, we see those shapes here and that transition set here. And that's the key here, is that we can do that. And so that's our reference. Now we're going to look at e-facies probabilities. And what we're going to do is simulate those probabilities in 3D and then get the maximum probability. And that's going to be our 3D facies. So we'll get the 3D facies after simulating into 3D. And okay, so here we have very spiky distributions shown. We have 4 probabilities of each facies. The first facies is P0, second facies is P1, and etc. And so the cross plots are here. They're highly nonlinear. They're not very nicely shaped, and we want to simulate and try to preserve some of that. And that's a bit of a challenge. If we just directly simulate, co-simulate these variables, we don't honor the distributions here on the right. What happens is it's basically, explained by the central limit theorem, or if you start sampling a nonlinear, non-Gaussian distribution, you tend toward a more Gaussian centered result. So that's not going to be acceptable. So we don't preserve shapes. Now I just want to touch on principal components. That sets the stage for what we really want, which is min-max autocorrelation. So principal components is taking a look at these two variables, v1, v2. This is just two variables, but it can be extended to multiple variables in a hyperspace. So v1, v2, they're correlated. We see the maximum variance direction is along this red line, and so if we solve for the principal components, we're looking at the maximum variance direction, eigenvalue, eigenvector, lambda 1. And what this is just a rotation to the maximum and minimum variance direction. So we would translate and rotate the space and have a new coordinate system. And then these two new component variables, factor variables, are orthogonal, or they're statistically independent. They're they have a correlation of 0, and so that is in the global sense. But when we take into account location, they're still spatially correlated. So we're looking for uncorrelated factors. We use this in various fields. I've used it numerous times with seismic attributes to look at what variables are correlated or create super variables and reduce dimensionality. But in this case, we're trying to get uncorrelated factors so we can simulate the variables and preserve shapes of distributions. And so as regionalized variables, which is how we're going to use them, they're spatially correlated. They have variograms. And so PCA only applies at a 0 lag value. When we start looking at then the what are called H-scatter plots, or that is the distributions at lag values on the variogram, what we see is the correlation in the cross variograms. So min-max autocorrelation is another method used to decorrelate, including essentially the variogram. And so here's the workflow we're going to use. So what we have then is the input probability values. We're going to normal score transform them, apply min-max autocorrelation, which is principal components, that is rotating the correlation matrix along with a lag matrix. So it's two PCAs essentially. And then we normal score transform those math factors and then simulate. Right? So if we have variables and we're going to simulate, we apply normal score transform and use a Gaussian type simulation. And we simulate as uncorrelated, so there's no cross variograms in these. And then we reverse the process. We reverse the Gaussian transform, the math, and the first normal score transform, and get our simulated p-values. And I don't have it on the diagram, but we renormalize as well. Make sure they add up to 1 at all 3D samples. And then we take the maximum of those 4 probabilities, and we get efacies. And these also show the transition characteristics. So this diagram is talking about how to handle spatial variables that are nonlinear. Multivariate nonlinear. And so here we have, in this example, I think I'm low on time. It takes too long to go through all this. the scatter diagrams for the p-values, and this is just showing the cross plots of, say, p-value, 0 to 1, 0 to 2. It's like a correlation matrix. Here are scatter. So it's a scatter plot, and it's highly nonlinear. Okay, so with PCA, this diagram is showing us that those p-values, say for 0 and 2, which are red and blue, have a correlation to factor 1 out of the principal components. In other words, they're similar. So what this diagram is a correlation circle. It's comparing the first and second PCA factors, and the center here is 0 correlation, and that outer circle is correlation of 1. So these are two probabilities are very highly correlated to the first factor. They're similar, whereas orange and yellow are have a correlation, opposite correlation on the second factor, and so they're behaving differently. So the conclusion of these images is that P0 and 2, red and blue, have similar relationships, and the yellow and orange have some correlation, and behave a bit differently, but they're definitely behaving differently. So here's the PCA factors now, and the distributions are a little better, but we're going to compare that now with math. So notice, we're getting some improvement in, look at those complex shapes here on that first row, and then these are a little better down here. Okay, so in the min-max autocorrelation, we have as I said, two covariance matrices. The first is the regular PCA, and the second is the covariance related to the lag values. So we're using the values at 0 lag compared, or the values compared to 500 meters separation. And so this we'd have to discuss varograms and show you the H scatter plots. But basically I looked, the range on the data was around 1 kilometer, and I took about a half. I tried a third to a half. It wasn't that sensitive. So here we get essentially a table that says the first math factor is a linear combination of the 4 input variables, which are those probability values. And this is what this matrix is showing, is we can store the transform, and then we can reverse it. This is going in the opposite direction. So now, looking at the math factors, it's still complex, but it's better. What we really want is a total shotgun blast, just a big circle. So again, it's improved, and the correlations are closer to 0, not perfect, but it's definitely improved it. Now we're going to apply an anisotropic variogram model, and we don't need cross variograms because they're treated as independent. So there's not a strong anisotropy in all of these. This is the vertical variogram, this other one back here. So just a modest anisotropy being used, and I ignored the whole effect. The check then is the input distribution of the math values and the output simulations. And so those shapes are being preserved here. Okay, this these shapes are essentially being preserved in the simulation. So that's the input well values on the left, transformed, and the output 3D model distribution of the probabilities. And then we reverse transform, go back to the original space, and compare the distributions. And we've done a pretty good job here of honoring the input distributions. So a lot better than the direct simulation. And then we renormalize, and there's the maximum probability. So we do see this transition where red and blue are associated with one another. We're mostly transitioning into yellow and then orange. So there's some stochastic variability in there. Okay, so final workflow is co-simulating petrophysics, and there it's just a direct use of the gamma density neutron, 3 curves. We simulate in 3D and then apply the Electrofaces model that was stored from the Mo code. And so we set up a full linear model, a co-regionalization. We applied a normal score transform first. And then we have this multivariate variogram model, similar scales to what you saw before. It's a little messy showing all the directions. And along the diagonal here are the primary variograms, and then the off diagonal are the cross variograms, the cross covariances, and we simulate in 3D. And so we're just, these are some of the rules. We combine the variogram models, adjust the sills, or we fit the primary, adjust the sills, and then ensure that the solution is positive definite. And we're going to check results, but here's the simulation we have. This is just summary maps out of the 3D, average maps over the zone of the gamma density, neutron, and the simulation. So it's a little dispersed, but the main rules hold. The transitions actually hold. So again, we've, through this method, honored the transitions as well. We'll take a look then at the checking. So in the checking, we have the 3 workflows. Inspecting these graphics, again, we have the red-blue associated transitioning into yellow and into orange as the dominant transition set. So here were the log proportions here that were input from the Electrofaces. Here's the one realization of the plurigaussian. And these can vary, depending on data sets, can vary plus minus 10, 20%. So just keep that in mind. But the general trend is that it's pretty close, because that's how a commercial software should work, unless there's something wrong in your setup. So here did inflate number 1 a little, drop number 2, and the other 2 are pretty similar. In the math method, working with the probabilities, there's some inflation of facies 1, that was the blue. The orange is similar, and the red dropped. Okay, using the petrophysics, we see a drift, quite a drift on that one. So that one could be adjusted. But again, it's the least nonlinear, or we didn't account for discontinuities of facies. It's kind of interesting. I didn't try to optimize this one, but it really dropped the proportion of the orange, and the red and inflated the yellow. So that could be adjusted, but then the transitions are being shown here. We have the vertical transition probabilities, the plurigaussian, again, the blue transitions into yellow, red, orange into yellow, and so forth. And using the probabilities, the transitions. And again, these arrows are the proportional to the facies proportion. The size is proportional to the facies proportion in the transitions. So we have the blue transitions to yellow and red with quite a bit of orange in this one. And the orange is mostly into yellow. Red is distributed across, but mostly yellow and blue. And then yellow into all three. So it's generally honoring the transition set. And this one really does. It's blue into yellow, red, orange into mostly yellow. But the proportions were skewed. So this is an exercise that shows you some options to work with. Again, this was an experiment, and there's room to optimize the process. So a last check then is the dispersion, and I used entropy, and we're not going to go too far into that. But it's something that's easy to calculate. And what we're looking at is really just the proportions of the facies and calculation. And so we can do this for a realization. We can do this across all realizations. So this is showing us that in this realization, in workflow number 2, we have this kind of entropy, and the high numbers are the more orangey yellow. And so that's where you see it's fairly dispersed here. So we're going to have a lot of variability in our realizations in these areas. And so it's a good check on the dispersion in your models. And it's kind of sets us up to a set of tools that can be used in geomodeling to actually check the quality of realizations. And when we're running scenarios, to actually help decide which sets of models are better in terms of behavior. And that's something none of the commercial software vendors have in their software, and they should add more on checking. So conclusions. The Electrofaces classification process provides us with auxiliary variables useful for alternative 3D modeling workflows. And those workflows, of course, it's when Electrofaces interpretation is acceptable. And it allows us to work with multiple scale models and grid-free models. So it allows us to go through scale change because we're working with 3D variables, even Electrofaces, although they're discrete at the log scale, they're more consistent with all the petrophysical parameters, and so those facilitate scale up. We demonstrated methods to model continuous variables and convert them to 3D facies. And this has implications for approximating nonlinear parameters like geomechanical parameters, geophysical parameters at various scales. Because take, for example, geomechanical parameters. If you take them from logs, you can't really scale them up directly. They don't scale as averaging parameters. Kind of like perm, you don't scale linearly. So finally, there's further work on quality measures using all realizations. That's something I've concluded from the study. And we want to be looking in our geomodeling software preservation of transition statistics. MPS and pluri-Gaussian help with that. The other methods don't do as good a job. Shannon's entropy is good for assessing dispersion of models. And another one that later paper I did, I looked at this Kullback-Leibler information divergence, which is a relative entropy, and it's to compare transition probabilities between different modeling workflows and lets us see which models actually behave better. So the key is to add realism into stochastic models, and we're looking at alternate methods, allowing us to deal with scales, etc. Okay, so that's the talk. Thank you very much, and we're a little over, so I'm ready for questions. And let's see.